Hi folks, we're going to take a look at number 40 from page 42 on the course review. Here we're looking at the number of bacteria in a culture, and the number of bacteria starts at 100,000 and ends up at 125,000 in 20 minutes. Okay. And what they want us to do is find the doubling time. So while they don't specify this in the question, because it's a population growth, I think they want us to assume that it's going to be an exponential model. Okay, so let's see what an exponential model would look like. So here we'll let y be the final population, k will be the initial population. Now, because we're interested in doubling time, it makes sense to use a base of 2. Okay, and we don't know what that doubling time is, so whatever our time value is, which we'll call x, we just divide that by the doubling time. Okay, so let's input what we know. So we know that the final amount is 125,000. We know the initial amount is 100,000, our base of 2, and the time elapsed is 20 minutes. And we see that the only variable that still remains unknown is d, the doubling time, which is what we're looking for. Okay, so it's just a matter of solving this exponential equation. Now, the main idea behind solving an exponential equation is finding a way to have a single exponential expression equal to some number. So we may have to use logarithms, maybe we won't have to if things work out nicely. So the first thing we have to do is isolate the exponential expression. Easy to do here because all I have to do is divide both sides by 100,000. So I do that and I end up with 1.25 on the left equals 2 to the 20 over d. Okay, exactly what I was hoping to get. Now, because 1.25 is not a power of 2, means I'm going to have to use logarithms to solve this. So I've got two ways I could do this. I could either take log base 2 of both sides, which is just the inverse function of what I have on the right. Okay, but because my calculator can't deal with log base 2, I'm going to have to then change the base. So since I'm going to have to change the base anyways, I'm just going to work with log base 10 right off the bat. And let's remind ourselves why we can work with the logarithm of any base. And it has to do with our good old friend, the ski slope rule, because now on the right-hand side, I can apply the rule to bring that down in front of the logarithm. So I have log of 1.25 equals 20 over d times log of 2. And then here it's quite easy to just solve for d. So I'll multiply d to the other side, and I'll divide both sides by log of 1.25. So I just end up with 20 log 2 over log of 1.25. And because everything is in terms of base 10, I can just calculate this on my calculator. Now again, had I taken log base 2 of both sides, that would have been perfectly fine. I would have just had to use the change of base of formula at some point. So I would have taken about the same number of steps. Okay, so let's calculate this here. So we've got 20 times log 2, okay, and divided by log of 1.25. Okay, and that gives us 61.13. Sorry, 62.13. So the doubling time is approximately 62.13 minutes. All right, so let's just recap here. So step 1 is to realize that population problems are usually solved using an exponential model. So number 2 was to choose our base as 2 since we're interested in doubling time. Then it was just a matter of inputting the variables whose values we knew and then solving an exponential equation, and in this case here, using logarithms. Okay, so that's it for this one.